Hello students, welcome to the online course on photonic crystals, fundamentals and applications. So today's lecture we will have a simulation demonstration of topological photonic crystals based waveguide. So the entire simulation demonstration will be shown in two different software. So today in the first part, that's why we are calling it as part 1, will be actually showing you the demonstration using a popular software which is COMSOL Multiphysics. Okay, and in the next one we will show you using another popularly used software which is CST Microwave Studio Suite. Okay, so here the main idea is to give you some hands-on experience. So we will be talking about terahertz topological based waveguide schematic slabs. So these are also photonic crystal slabs as we have discussed throughout our course. So here you will see that we will be mainly focusing on the three major aspects. The first one will be how to obtain the dispersion diagram for the unit cell, then how to obtain the topological edge states, okay, in the dispersion diagram, and then finally we will go for the simulation of the complete waveguide structure. So for realizing a topological based waveguide, we will basically require all the simulation steps which are the basic requirements. So now if you consider any periodic system, it can have these two types of unit cell representation. So you can think of a rhombic unit cell that is used. So you can start with this point being the origin 0 0, and this one will be minus a comma 0. This point is minus a comma root 3 a by 2, and this point being minus a by 2 comma root 3 a by 2. Okay, so this particular distance is basically root 3 a by 2. What is a here? A is basically the lattice periodicity. You can also consider this another representation, that is a hexagonal unit cell. So hexagonal unit cell you can draw like a rectangle which has got the length of a and the width of a by root 3, and then you take this rectangle and rotate it by plus 120 degree, you will get this rectangle, okay, and then you rotate this horizontal lying rectangle by minus 120 degree, you will get this particular rectangle. So when you add up all these three rectangles, you basically get this hexagonal unit cell, right? So here we will first consider the unit cell which has got two inverted asymmetric triangles. As you can see, the triangles, these are like equilateral triangles, so every side is of equal length, but this guy the length is L1 and this one the length is L2. Okay, so L1 was taken to be 0.65a and L2 was taken to be 0.35a. What is A? A is the lattice periodicity. It is taken to be 242.5 micrometer in this particular example. Now we have kindly go through the earlier simulation of the topological photonic insulators. You will see that for the K vector sweep we require these two conditions, okay, alpha and beta for different ranges of K. Okay, so these basically are the conditions given for the wave vector K that will be used for sweeping the irreducible Brillouin zone. That means we have to go from okay, this has to be corrected, it's from gamma to M to K to gamma and so on. So this is the rhombus geometry unit cell that you have seen. This is basically taken by connecting the centers of the four hexagons, as you can see here. Okay, so if you can put the triangular shapes okay, as geometric holes which are basically etched from the rhombus shape silicon structure, you basically get one type of unit cell. Okay. So this is the symmetric design where you have the two triangular holes to be of equal size. So in that case there will be no band gap, so the band gap will close at the K point of the Brillouin zone. But in case if you introduce asymmetry, means one you keep as it is, but one hole, triangular hole, you shrink in size. In that case the band gap opens up and an edge state will appear inside the band gap, and that will allow the propagation. Okay. So we will call this type where the larger triangular hole is on the top, okay, and the smaller one at the bottom. We can call this as unit cell 1, okay, or you can say this is VPC type A. Okay, VPC is basically valley photonic crystal. Okay, and if you flip this design, okay, if you take a mirror of this design, okay, that is where the smaller triangle will come closer to the smaller triangle. Okay, this particular unit cell can be named as unit cell 2, that is valley photonic crystal B. Okay, so why we need to do this? When you have these two types of unit cells making a boundary, you are getting an interface, and this is where the topological edge states can propagate through. Now, to check the presence of the edge states, we will perform simulations of the supercell array structure of the unit cell design. So you take the unit cell like this and then repeat 4 of this. Okay, so you can mark this box. Okay, that is basically the supercell that can be extended infinitely, and you can get the characteristics of the first any one type of the photonic crystal cells like this one. So we are just considering this case. Say you have VPCA, you have taken 4 cells of VPCA, and then you can actually arrange this supercell structure in the form of an array of strip. Okay, why we do that? If you do that, you can use the eigenvalue simulation for the wave vector K in COMSOL multiphysics software, and that will give you the edge states. So you will be basically calculating for all these different points. So this is the gamma point, then this is the K prime, K prime, K and K prime, and so on. So these are basically coming from those different adjacent cells. Okay, so these are the important points for which you have to calculate, you have to do the eigenvalue simulation to obtain the edge state. So all these things we will be seeing in the video demonstration that I will be showing you right now. Okay, so I will show you the video demonstration using COMSOL multiphysics, and that will cover all those different aspects that we have discussed. So it will show you how the dispersion diagram of the unit cells are obtained, how the topological edge states are calculated, and then we will go for the simulation of complete waveguide structure. Okay. So our TA for the course, Dibaskar Biswas, will take you through this particular video demonstration, and that will give you a complete idea how you can go ahead from the scratch to design topological photonics based waveguides.
Hello students, so this will be a demonstration video, the part 1 for the simulation of topological photonics based the waveguides, basically in the actually terahertz frequency region. So basically in this demonstration, actually this simulation demonstration is of actually 2 parts. So in the first part, actually we'll be watching, we'll be actually doing the analysis of the band diagram of the unit cell, and also the edge state analysis or the edge state dispersion diagram of the same, that is of the same design, whatever unit cell design we'll be discussing here. So we shall be analyzing two main things here in the first part. So in the second part, here in the first part, the software that we'll be using, it is commercially available console software. And in the second part, actually, we will be designing the waveguide structure based on the topological valley photonic crystals. And based on that, we shall be analyzing the transmission analysis. We shall be doing the transmission analysis of that entire photonic crystal slab structure, and that will be doing it on the CST studio suite. So actually, so in this video, so as you can see that I have opened the console software, and you can see that after clicking on the console software, it will show you this interface. This is a kind of interface, the opening interface of the console. So you can see that in the top left corner, you can see that here this model wizard and blank model, two options are there. So blank model is generally it's not required actually. It is for more advanced applications, advanced designing for building applications, actually application oriented actually designing. So we don't require this for our purpose. Only model wizard actually is required. So we'll be clicking on this model wizard. Now you can see that there are many interfaces of console. So you need to select the space dimension. So that is in what will be the space dimension that will be working, whether it is 3D or 2D or 1D or even the 0 dimension also. That is the point. So you have the 3D option, first option, then you have the 2D axis symmetry, that is along the across the Z axis. Then you have the conventional 2D space dimension. Then you have the 1D axis symmetry. Then you have the conventional 1D and the 0D. So for our purpose, so we actually do the band diagram analysis of the unit cell for the 2D actually structure. So for the 2D unit cell, we will be doing all the analysis. That is the dispersion diagram of the unit cell or the band diagram, and also the dispersion diagram of the edge states. So both will be done on the 2D platform. So we will be clicking here on this 2D option here. Now after clicking here, so after selecting the space dimension, so now console will be asking for selecting the physics. So physics is an important tool because whatever analysis, whatever simulation you will be doing on a particular space dimension or on a particular after selecting the space dimension, you will be requiring the physics. That is every simulation that you perform. So on the background, actually, what happens is that the software performs some mathematical calculations or mathematical analysis. So this is particularly based on the particular physics that you choose. So that's why here you can see in the console there are a list of physics that are actually there. So right, starting from the SE to DC, then acoustics, then the chemical species, transport, electrochemistry, fluid flow, heat transfer, a lot of physics interfaces are there. So for our purpose, we actually select this radio frequency. We expand this option. And then on the third option, you can see that is the electromagnetic waves frequency domain, that is the EMW. So we require this physics interface. So we click here, and then in the add button, we click the add button to add our physics interface on this blank window. So after, as you can see that now after adding this, it will show the electric field components, that is the EX, UI, EZ. So we are working on so that is the possible electric field components that will be doing the analysis here for this particular physics. So after adding the physics, we shall be quickly moving to the next part, that is the study. So we'll be clicking on the study button, and then you can see that there are many sort of analysis options are there. So in our case, actually, we need to do the eigen frequencies analysis. That is because we are actually required to find the dispersion diagram, and dispersion diagram is nothing but the plot between the eigenfrequencies. That eigenfrequencies is nothing but the allowed modes inside that particular structure. Okay, so whatever units we will be designing, there will be certain allowed the modes or the frequencies that will be allowed by the structure. So these are known as the eigenfrequencies. So this dispersion diagram is the actually the plot between the eigenfrequencies versus the wave vector. That is the k vector or the wave vector in the structure. Okay, so this study will be the eigenfrequency. So we'll be selecting this study here. And after selecting this, you go to the bottom part and then this done option, click the done option here. And it will take few seconds here. So you can see that this is the typical interface of the console. So this graphics is the working area where you can visualize your design. And then this is the model builder where you can see some specific interfaces actually have been set up by default. So you can see that in the global definition, you have the parameter where you will be defining all the parameters which are necessary for your design. And then in the geometry option under the component section, so you will be defining all the blocks or the polygon or whatever it is. So you will be basically will be designing our model here. Then after designing the model, we will be moving to the material part where we will be adding the material, okay, for the structure. And then in the physics, under the physics, we'll be we'll be making all the changes. We'll be actually inserting the boundary conditions here that we'll see it later on. And then after doing all this, we go step by step. So we go down and we can see this mesh. So meshing is actually a very important aspect for particular for all these actually simulations. Why? Because what actually meshing does actually in the simulation. So probably you all have studied about the Maxwell's equation in the electromagnetic field theory. So what Maxwell equation does is that it gives us it correlates the time varying electric field with the time varying magnetic field actually. That is the last two equations. So these Maxwell equations that we read in the in our textbook, these are all for the infinite cases. That is, we are considering an infinitesimally that is infinitely big, or we can see that for a continuous body. Okay, for continuous structures, we are actually using those equations. That's why you can see that these are the integral. The Maxwell's equations are in the integral form or in the del form. But whenever we are dealing with practical structures like the discrete actually structures which have finite size, so they are actually the Maxwell equations take the discrete form. So in the discrete form, what the software does is that it actually breaks down. What meshing actually does here, that it breaks down that particular structure, whatever it is, be it your 2D structure or the 3D structure. So it breaks down your structure into a very small finite component. And what it does is that it for that particular small component, for each component, it will solve the Maxwell equations using all the necessary boundary conditions, and whatever result it will get, it will store it in a particular matrix, and then the further analysis actually the software does. So that is how actually meshing becomes an important aspect, because if you do coarse mesh, coarse means the meshing is not of high quality. So if the meshing quality is not high, then it will produce error in your results. And if the meshing quality is very high, so obviously you will get very good result, but the simulation computation time actually will increase drastically. So that actually sums up the importance of the meshing in the simulation. So after doing the meshing part, we'll be moving to the study part here, where we'll be doing the parametric analysis of the wave vector k. So I already actually in the previous lectures, I already showed one demonstration of photonic crystal slab, where actually creating the defect, line defect, we showed we designed a waveguide, and we showed the band diagram there, where actually I showed there the how the brilliant, the irreducible, how the k vector is actually swept across the irreducible brilliant zone. So here also the actually the concept is actually basically same. So the same concept actually applies here, but there are some new things to be learned here. So I shall be discussing all of that. So we'll be in the study part, we'll be doing the parametric simulation of the wave vector here, and then after that we'll be going to the eigenfrequency option, and in the eigenfrequency option we'll be choosing the desired number of eigenfrequencies. So we'll be just keeping it, we'll be restricting ourselves to only two eigenfrequencies. That is only the first band and the second band, because we just need to see whether for the symmetric case whether it is meeting at k equals to 2, that is the k symmetry point, and after breaking the symmetry whether it is creating the band gap or not. And then search for eigenfrequencies will be typically keeping it at 1 gigahertz only. So 1 is the actually default value for the COMSOL, actually for the eigen mode solver, and gigahertz is the unit because we'll be basically it's actually the terahertz range, but it is either of the range of 250 to 350 gigahertz. So that's why we are taking the unit as gigahertz actually. And this will be the eigenfrequency search method will keep it as larger real part, because if we take other values options here, so the complex eigenvalues actually will appear, and that will give error in our analysis. So that is pretty much about the basic interface of the console here. So now we shall be defining all the parameters for designing the unit cell here. So first we shall be starting with the lattice periodicity. So that is the the lattice periodicity is your A actually. So we'll be defining here, that is 242.5. Then you give third bracket, then you in place of micro, so micro symbol is actually replaced by U, is denoted by U here in console. Then micrometer M, and close the third bracket, and then you click tab on your keyboard, then it will take the value. Description you might enter it as lattice periodicity, or it is not required that much, it is not that much important. So after that you need to define alpha and beta here. So alpha is basically the if else condition here. So if k less than 1, so the value will be your 0.5 into k. Else if, then first bracket starts k less than 2, then the value will be 1 by 6 into k plus 2, first bracket closed for that k plus 2. Else the final value is 2 by 3 into 3 minus k. So bracket close for 3 minus k, bracket close for the second if, and then bracket close for the final if. So you need to ensure that all the brackets are getting closed, otherwise you will be getting a red symbol just like this. So your entire if else condition will appear red because of some error. So if it appears like this, you just, what you need to do is that you just put the cursor on that if else condition, and it will show what is the error. So here you see the error is unknown model parameter k. So this is because we have not defined k. So that is why console is actually showing the error. So we'll be defining k here, but first of all let me define alpha and beta, and then we'll be defining the k accordingly. So for k less than 1, so it is actually pretty much same. Let's see if k less than 2, then it is, I think 1 by 6 into 4 minus k, or else the final value will be this, 1 by 3 into 3 minus k. Okay, now we shall be defining k here. You just give any arbitrary value, 0.1. So it will take, now see the red color on the statement, the red statement has actually turned black. So it means that our the error has actually, we removed that error. Okay, then you need to define k naught here. So it is your 4 into pi divided by first bracket square root of 3 into a. Okay, Fine. Then you define AX here, so it will be alpha into K naught into square root of 3 divided by 2. Okay, and then accordingly Qi will be your K naught into beta minus, then again bracket 0.5 into alpha. Okay, then you define your L1 and your L2 here. Okay, so what is your L1 and L2? That will be just let me define all those points here. M is square root of 3 into L1 by 2. Then N is your square root of 3 into L2 by 2. And your then P. P is your A divided by square root of 3. And then Q is divided by square root of 3 into A by 6. So you might wonder, you might be wondering that why I have defined all these things. So L1 and L2, you can see it from the presentation, the PPT file itself. So you can see that this is the rhombus unit cell. These are all the coordinates here of the rhombus that will be inserting all will be defining the rhombus in the console. And L1 is the length or the side of the big triangle, equilateral triangle, and L2 is the side of the small equilateral triangle. So this rhombus will be filled with silicon, and these two triangles will be the triangular holes. So we'll be filling those triangles with air. Okay, and these are the alpha conditions actually. So how we are actually getting these alpha equations that I have explained it in detail in the photonic crystal slab, I think in the photonic crystal dielectric photonic waveguide actually. So in that lecture series, I actually also showed the demonstration of how the line defect, using line defect, we can create a waveguide. So there I have explained in details regarding how from where this alpha and beta are coming, and also the regarding the complete Brillouin zone and also the irreducible Brillouin zone. So all these things are there. After this defining here, so we will be moving to the geometry section. So in the geometry section, an important thing to note here is that the length unit. So you change it to micrometer, otherwise some error might be there. Okay, so you expand the geometry here, and then you go to the geometry on the top, and then you click polygon here. Okay, so you name it as rhombus. So put the coordinates here accordingly, minus a 0 and minus 1.5 into a. Okay, square root of 3 into a by 2 minus 0.5 into a, and you hit build all objects. Now you can see in the top there is called zoom extent. So if you click it, it will zoom out your figure. So you can see this is the rhombus structure. This is just a closed curve structure. This is not a solid one. So for solid one, you can see that the sketch option is on here. So you just click it and off it. So you will be coming out of the sketch mode, and see now you will be getting the solid structure, rhombus structure. So I have I have inserted all the coordinates of the rhombus. So these coordinates are already there actually, and A is the lattice periodicity. So after designing the rhombus, you click, now you have to design the two triangular holes. So basically the two triangles. So you need again polygon, and you write here big triangle. I need to enter the coordinates of the triangle. So it's a bit tricky one because we don't have we directly don't have all the triangle option here in the console, and we simply cannot draw a line and then rotate it twice to get an equilateral triangle. That is also a difficult process, and it will not give proper equilateral triangle. Also you need to keep in mind that this you can see there are two midpoints. So one midpoint actually its distance from the base of the rhombus is a by root 3, and another midpoint its distance from the base of the rhombus is root 3 by 6. So we need to ensure that whatever triangle you are designing here, so its midpoint should be one of those two midpoints. Okay, so for big one, so this will be big triangle, this will be this is the midpoint, and for small triangle this will be the midpoint, and vice versa for the BPC unit cell B. Okay, so to get such kind of accurate geometry, so it's a bit difficult. So there are not so easy process that you can directly get the equilateral triangle. So we'll go by the coordinate method here. So we know that in the equilateral, the midpoint actually, so the midpoint behaves as the centroid of the equilateral triangle, and it divides the perpendicular bisector. So if I go into this presentation mode, and if I use a pen, so this is typically your equilateral triangle here, and this will be the perpendicular line. So there, this is the centroid. So this is 2 by 3 of this L, and this is your 1/3 of L. Okay, and this is the entire L is this, and you know this entire L, this is nothing but your root 3 A by 2, where A is your side length of the equilateral triangle. Okay, so this is the centroid point here, and this is the okay. So this will be the base of the rhombus, base length, and from this center to this distance. Yeah. So this is the distance, and this is given by A by actually root 3 here. So we require 3 coordinates for the equilateral triangle. So this coordinate, then this coordinate, and this coordinate. Okay. So for this coordinate, what you need to do is you just simply subtract this A by root 3 minus this 2/3 of L, isn't it? So from there, actually, we'll be getting the y coordinate for this point, this distance, and this distance is nothing but the y coordinate of this point. X coordinate actually is pretty much easy, because it is just nothing but the minus of A. Okay, so that is how you get, and for these 2 points, actually these 2 points are very now what will be this, so minus A is the point here, X coordinate, and you move further in the positive direction by an amount A by 2. Okay, so it is nothing but your minus A plus A by 2, this is the X coordinate, and Y coordinate will be, you just add, so your A by root 3 plus, okay, A by root 3 then plus this distance, 1/3 of L. Okay, and then this will give the y coordinate of this point. Similarly, the y coordinate of this point will also be same, only the x coordinate will change. Now you have to, in place of plus A by 2, you need to go minus A by 2. Okay, so I think the coordinate, how to get the coordinate, it is clear. So I'll be discarding this. I'll be going again. So you need to now enter all the coordinates here. So I have actually already designed that particular thing, structure. So here in the big triangle part, also in the geometry part actually. Okay. Yeah. So in the geometry part, big triangle. So what I'll do is that, so you can see that minus a p minus 2 by 3m. So whatever I have defined here, actually p q I have defined here. So that's why to make our analysis easier, because if I go on writing a by root 3 minus 2/3 of root 3 L by 2, so this will make it very lengthy process, and it will be time taking. So I already assigned those a by root 3 by L as variables here, and then I have done this analysis. So I'll be copying all those points here, and then I'll be taking directly here. Paste. So this will be build all objects. Now see. So this is the big triangle here. So similarly for a small triangle, we'll again click polygon here, and then small triangle. And then we'll be clicking the build all objects. So this is the two triangle, and this is the symmetric case, as because we have taken L1 and L2 as same here. So we'll be checking the symmetrical case, and then we'll be doing the asymmetric part. Okay, so after doing the analysis here, doing the geometry analysis part, now we'll be assigning the material. So in the material option, now you know this that the triangles will be filled with air actually. So in the top option, you can see that material option is there. You go click, and then you click add material. So in the add material, you option is there built-in. So in the built-in, you expand it, and then you click air, and then you click add to component to add the material under the component section. So once the material is entered, you just close this add material. Okay. So now you can see that I think I closed it. Okay, fine. So I think I think it has certainly the application has crashed actually. That's why the simulation window has closed automatically without getting saved here. The file I can't see here actually. Okay, fine. So we'll be going on with this actually. So you can see that these are the two materials here. So this is the air which will be filled with the triangles. You can see this is the two, and this is the third domain. Okay, so one is actually, you can see it is overridden, so you can simply delete it by clicking the minus symbol. And silicon, so you just need to see that here we are taking the refractive index of the silicon as actually 3, and for air it is 1. So initially when you will be adding, so for silicon you won't be getting such kind of that by default the default value of the material of silicon material is not this in your console. So you just need to add a blank material here. So again in the material section, you just click add material, and then you click add blank material. So in the add blank material, you define the refractive index only. You define the refractive index as 3, real part, imaginary as 0 because we are taking lossless, and you define the electrical conductivity as 10 to the power minus 12, and all values will be coming by default. Okay, so by default, as you will be selecting the blank material, so it will here actually relative permeability and relative permittivity. These all will come. Refractive index will not come. So what you need to do is that you go to this physics EMW, and then you go to wave equation, and then you click in the electric displacement. In place of relative permittivity, you just click refractive index. Okay, so this will change your material contents of the silicon to this part, and then you enter the value. So after assigning the material, you go to this EMW, that is the physics interface, and here by default this will be there, 3-component vector. But here we actually were not doing the analysis for the 3-component vector here, because this is a 2D structure, and we are mainly concerned with either the TE mode or the TM mode. So here we are doing the analysis using the TE mode. So you just keep in mind is that in plane vector is the TE mode, and out of plane vector is the TM mode. So for TE mode, you just click the in plane vector. Okay, so after doing this, you click here on the physics interface and then you click on periodic condition, right click and then click on the periodic condition. This will appear. So you select this edge and its opposite edge, because these two are actually are paired edges, and so correspondingly this and this will be the two paired edges. So you select those two edges, and then in the uh, type of periodicity you choose flocket, and then you give enter kx and ky. Okay, similarly you do it for your periodic condition 2 here. So in the periodic condition 2 you select these two options and then you click on kx and ky. So after doing this, you will be coming to mesh here. So in the mesh, you can see that this is the physics control mesh and the user control mesh. So physics controlled mesh actually basically is the actually the physics will control your meshing quality here, and whatever physics you enter, that is the EMW or the wave optics or whatever it is. So it will be controlled by the software itself. But sometimes the physics control mesh actually does not give proper mesh quality. So therefore, because in that case, in this case, if I you can see if I select physics control mesh and then if I click, it is now you can see that this is extremely fine. So this is the highest quality mesh for physics control, and if I click build all, so you can just wait. You can see how worse is the mesh. So the mesh quality is very bad. So you just have to go for the user controlled mesh. So user controlled mesh, what you do is here, you make it to predefined and then you go to finer. Finer will be because finer is sufficient for us. And for size 1, that is the entire silicon part, again predefined, and you go to finer. And then size 2 is the edges. So you just predefine and then go for finer actually. And then rest of the other things you don't have to do anything. Okay, so after doing the mesh, you go to the study part and then you click the study and then right click, and there you will see the parametric sweep option. So in the parametric sweep option, this type of will come. In the sweep type, by default it will be specified combination, so you have to make it to all combinations. And then there is a plus option called the add. You click here and then from the list you select the k value and then click here and then click this. This is the range. So in the range, this is the entry method. There are the entry methods are like in step value or number of values or logarithm. So you keep it as step and then you start your k value from 0.1 and you end it with 2.9, and the step you take it as 0.01. So why do we take 0.1 and 2.9 instead of 0 and 3? You can, if you might remember this, because we sweep the k vector from 0 to 3. Okay, that is covering the irreducible Brillouin zone. So we do this because at the extreme value, that is 0 and 3, so there are some discontinuities in the band diagram, and such discontinuities will appear in the band diagram, which will make it look ugly. So it will not be a proper and authentic band diagram actually. So that's why we ignore those extremes, and then we start from a little slight deviating from the discontinuities from the extremes. So that's why 0.1 and 2.9. So after that, you click on eigenfrequency, you select the two bands, keep it as 1 gigahertz and then larger real part. Okay, and then you click build all, and then you click on your build mesh, and then you click compute. So as you know that this is the symmetric case. So for the symmetric case, the band will actually meet. So we'll quickly, so as the simulation actually it runs. So now we shall be discussing about the edge state analysis. So what is this edge state here? So you can see this is the VPC K or unit cell 1, and this is the unit cell 2. And when we bring them together, this is the interface. So we have already discussed this in the previous lectures also. That whenever we bring them together and at the interface actually some interesting phenomena will happen, and that is and this is the beauty of topological photonic crystal. So what it does is that if we see the band diagram, So we are now discussing about the band diagram for the individual unit cells. If you take this kind of pair, okay, and then you take the band diagram of this kind of combination. So we can see that the band gap. So this is the asymmetric unit cell, and this is also the asymmetric unit cell. So this two will create a band gap opening. So inside the band gap, actually a fine line will appear. Uh, okay, it is basically, it is typically a single line. A single line will appear, a curved line will appear, and this actually represent the topological edge state. So this confirms the fact that inside the band gap, the signal transmission will occur. Why? Because the input signal, the input field mode, this will excite actually. Uh, so as we'll be doing the simulation analysis, so the input field mode actually will excite the edge state, okay, in that particular band gap, and that due to that excitement, the field transmission will occur for that particular band gap frequency range, which in normal insulators it does not happen because there is a complete band gap. So there is absence of such edge states. Okay, so after that, we shall be so this is the kind of structure we'll be doing the edge state analysis. So this is the kind of supercell structure. So in order to do the edge state analysis, you need to take four kind of rhombus unit cells together, and then you need to join them. So after joining them, you can see that the violet part, as you can see, the violet part, it represents the unit cell supercell structure. So you need to make an array of this structure, and then you do the dispersion analysis. So you remove this unwanted part, which are the unwanted parts which are outside those this purple rectangular box. And this is the complete Brillouin zone, and you know how these points are calculated using the lattice vectors and also the reciprocal vectors, and then using the formula, transformation formula. So this k point is actually 4 pi by 3a, and then this k dash is actually 2 pi by 3a. So and this k point is actually minus 2 pi by 3a. That is basically minus 0.67 pi by a, and this is 0.67 pi by a. So we will be for this edge state analysis, will be sweeping the k vector from your minus pi by a to pi by a. So we just want to make sure that k dash, this point and this k point gets covered in our edge state analysis. So that's why we take the slightly above this 2 pi by 3a. Okay, both slightly above this 2 plus minus 2 pi by 3a. That's why we take it as minus pi by a, slightly above minus 0.67. Okay, so we'll be, I have already simulated this. So I have already designed this and actually simulated this structure. Why? Because this simulation is one of the most difficult simulations in topology. Why? Because here the simulation time for a normal mesh also, I'll be showing you what mesh I have taken. So for a normal mesh, it takes around more than 22 hours. So this such is the huge amount of time it takes. So often what happens is that if you increase the mesh quality also for getting accurate results, it takes more than 1 day. That is, it takes around 30-35 hours. So that's why I have already simulated the results, and I will show you how I have done it. So in the parameter, the lattice periodicity alpha, beta, kx, ky, the k and k naught remains the same. Only in the kx and ky, you simply just take kx as k into pi by a, and then we'll be sweeping the k from -1 to 1. So in that case, you will be sweeping the kx vector from minus pi by a to pi by a. Ky, actually we are taking it as 0 because we are not interested in the vertical direction. We are interested in the horizontal direction, that is along the interface. So we are just interested in the interface part. So that's why we are keeping ky as 0. Then L1, L2 all are remaining same. So in the geometry part, after making this, okay, after you designing this this rhombus, what you do is that you go to geometry and then you go to transform and then you click move. So in the move option, what you do is that you select all those what you say is that you select all those the rhombus and the triangles, and then you click build selected. Okay, and the displacement vector is actually a, because it is shifted by a distance of a actually. So the same rhombus will come here, and then again move to and select this, and then you click build selected. Now what you do is that displacement you specify positions. So your old vertex will be this. This is the old vertex, so this should move here. So that is what you are doing is you are shifting this rhombus to the upper portion. Okay, so your vertex, final vertex will be this, and then you click build selected. So you will get the third of the rhombus here, the unit cell here, and then you click on again move, and then you do the same thing. So you will get this four kind of structure, so which is similar to this thing. Okay, so now you need to make this rectangular box by removing all the unwanted thing. So what you need to do is that you take line segment. In the more primitives option, you click line segment, and then you take the vertex here. So this and starting vertex and end vertex, and then you click build selected, and then again line segment. Okay, now what you need to do is that these are all domains. So these are called domains actually. So you need to divide those domains into, you need to separate them so that you can delete those unwanted parts. So you go to booleans and partitions, and then you click partition domain. So you will arrive at this. You select entire structure on except these two lines, two straight lines, vertical lines. Okay, so this is the domain to partition. So and what will be the particular object that we will be doing the partition with? So partition with will be the edges, that is the two vertical lines. So here you select edges, and then you select all those two vertical lines, and then you click build selected, and then here delete option is there, you click delete. So the delete by default object will come, so you click on you click on domain, and then you select this. Okay, now see, so these domains have been separated. So you select all those domains, and then you click build selected. Okay, so now you are getting this unit cell structure. So this is similar to this purple box. Now what you need to do is that this red line boundary and this red line boundary, you need to remove this. So what we do is that you first do the union. So in the boolean and partition, again you go to union, and then you click union here, and you just select only those parts, not the triangles, and you just keep them off, keep them unchecked actually, keep input objects and keep input boundaries unchecked, and then you click build selected. So you will be removing that particular boundaries, and then again on union 2 you select all those triangles to merge with that particular rectangular box. Here you keep the interior boundaries at checked, otherwise the entire C and that structure will go. So just keep it as like this. Okay, now you make the array. So this you select, and then you repeat it in the vertical direction. Typically we take it as 15 times, and the displacement vector will be your, in the y direction it will be square root of 3 into a. Why? Because this is the rhombus. Okay, so the rhombus height is square root of 3 into a by 2. This is another rhombus, so it will be twice of square root of 3 into a by 2. So this 2 gets cancelled. That is why the displacement is root 3 into a. So after clicking this, you will get the strip, okay, in the upward direction. Now what you need to do is that, so this is actually for the entire AB part. This entire strip is of the your VPCA, repetition of VPCA. If you can see this, So this is the big triangle, this is the small triangle, this is the big triangle, this is the small triangle. So this actually gets repeated in the upper direction. So this is because this all 4 unit cells are VPC-A. So this is, if I take highlight. So this is your interface. Okay. So beneath that, you have to take the VPC-B portion. So similarly, a similar thing you will do it for VPC-B like this, making 4 options, and then you remove this, take the line, and then you remove the unwanted part. So this will be a time-taking process. What shortcut is, you just make this supercell and then you flip it. Okay, this will give you the VPC-B configuration, and that's why after that you do the union. So you take all the union of the array, and then you take the mirror. So you select this entire array, and the mirror, the line of reflection. So this is important. You choose this edge. So along this edge, mirror analysis will be done. See, now this upper portion is actually the A type, and from there, this is the interface. So this is the interface, and from this interface to the bottom, the B portion comes. So this is basically the AB type. AB type state configuration. Okay. Similarly, you fill all those triangular holes with air, and then this with silicon. Then you go to electromagnetic waves, and in the periodic option. So in the periodic option, actually you select all those edges, don't miss them. Select all those edges, and then you here you define as flocked periodicity Kx and Ky, and you take scattering boundary condition here, and in the top part. So in the top part and also in the bottom part, to give it as a scattering boundary condition, because here periodic condition won't be applied because you have already hit the boundary of your slab structure. So this is only a single strip. Okay, and if it now to get the final slab structure, what is the basic thing? You need to repeat this strip in the right direction, in the right hand direction, and also in the left hand direction. Okay, you don't need to repeat this strip in the upward and downward direction, because already you have hit the extreme of your slab structure. So that's why we are using the scattering boundary condition here. Okay, and then after scattering boundary condition, all those have been applied, you just make sure that this is in plane vector, because sometimes 3-component vector, it stays there by default, and then your simulation will not run. It will give erroneous results. Okay, so make sure that this is in plane vector is selected, and then you go to mesh. So in the mesh, actually you take physics control and then normal, because if you, by any chance, if you increase it to like finer or extra fine, your simulation time will increase drastically. So it might take even 2 days also. And also it's not only about the simulation time, it is also about uh, the how powerful your PC or laptop is. So like my operating system is running on i5 12th gen with 16 GB RAM. That's why it is able to handle uh, that much amount of mesh here. So, and even with that configuration, it is taking at around 22 hours time. So if you have configurations lesser than that, so just make sure that you don't you just keep physics control mesh here, and you do the analysis in the normal mode. Okay, so after clicking selecting the normal mesh, you click build all. And in the study option, you select this parametric sweep, and then you sweep it from -1 to 1, and the step size is at 0.01. You sweep the K vector, and in the eigenfrequency analysis, you search frequency, you keep it as by default larger real part, and then in the number of eigenfrequencies, you take it as 110. I generally take it as 110. It is not like a default number. You can take it whatever number you want, but it should be greater than 100, because if you can, if I can show you here, let me, yeah, fine. Let me show it here. So eigenanalysis will be coming like this. So these are the lower bands. So a lot of bands will come. Okay, so a lot of bands will come, and these are the upper bands. A lot of bands will come, and this will be the band gap. So inside the band gap, such kind of edge state will appear, a single line. Okay, a single line will appear, and this you can see. This will actually confirm that your structure is logical behavior. Okay, so for AB type design, this might be the edge state. So for BA type will get such kind of opposite characteristics curve. Okay, so why we are getting this opposite here, and some interesting phenomenon happens here at this point, intersecting point, and at this intersecting point, this will be discussing it. So a lot of eigenbands will come. So that's why the simulation time takes so much time. So that's why you keep the number of eigenfrequencies as much higher as you can. So that way by default you take it greater than 100. Okay, and then you click on you go to home, and then you click on build all, and then build mesh, and then you click compute. So I have already done the simulation analysis of the edge state, and you can see that this is for the AB type, there is the red one, and for the BA type. So as I have already told here, you can see at this intersecting point. So this intersecting point are nothing but, if you take the exact analysis, so this is the plot in that I have done. So I have extracted the data and I have plotted in origin. So if you take a single straight line in the origin and you can check the x coordinate, you will get it as minus, that is 0.67, and here it is minus 0.67. So you can see that the graphs are actually contrasting in nature. How it can be visualized, if you take the tangent at this point, the slopes will have opposite values. Okay, equal and opposite values. So this means that for your AB type and for your BA type designs, the slope of the curve is given by the group velocity. So for your this slope, the group velocities, actually they are for these two modes. Okay, so for this two type of designs, okay, for the two type of configuration, the group velocity will have actually uh, these two configurations will have opposite group velocities, and that's why they will not couple with each other. So that inter-valley mixing is actually absent here. Why we are calling it as a valley here? That is because this at this point actually it looks like a valley actually, and this point corresponds to, if you can remember, this point actually corresponds to k dash, and this point corresponds to k point. So if you go to this, see, so this is k dash is nothing but 2 pi by 3a, that is 0.67 pi by a. That's why this point corresponds to k dash, and this point corresponds to k. So that's why they are known as k valleys, k dash valleys. That's why they are known as the valley points. Okay, or you can say it as and that's why that is and that's why we call it as inter-valley mixing. Inter-valley mixing is absent. That's why the propagation losses is also less, and that is the beauty of topological photonics. So, and actually I have extracted the data and I have plotted it in origin, because the data extraction becomes a huge headache actually for this simulation, for this topological edge state simulation, because after finishing, if you try to export the data also, the file size will be typically of the order of 20 to 25 GB. So it's a humongous file, and that will not be opened even, that is your default software, that is a notepad, it will not be able to open this kind of huge file size. So for that you will be requiring the notepad plus plus. So notepad plus plus actually can open this kind of huge file size, and that also actually it will take a lot of time. It takes around 15 to 20 minutes depending upon your how powerful your CPU is. So in a nutshell, actually this topological edge state analysis is one of the most important also, and it is also one of the most difficult analysis in the entire topological photonics simulation part. So I think our simulation has got over. Okay, so for the symmetric case, we'll be checking the band diagram here. So we covered the band diagram analysis, and also we covered the topological edge state in this first part. And in the next part, the demonstration will be seeing how, so based on these simulations, we'll be designing the entire the waveguide structure. So this the interface. So the interface will behave as the waveguide, and we'll see how the terahertz signal actually passes. So you can see that for the symmetric case, now see the two bands actually are meeting at k equals to 2, and this k equals to 2 corresponds to the k symmetry point, okay, in the Brillouin zone. So that's why this point actually it is the band is actually meeting. Now what we'll be doing is that if you take it as 6.5 and if you take it as 3.5, so now you are actually breaking it. Okay, so now you are breaking the symmetry. So now the band will open. Okay, so I think we need to wait for another I think 6 to 7 minutes. So this is the kind of edge state analysis. You can see that how dense is the mesh. Although it might appear that the mesh quality is dense, but if you zoom it, you can see that this is the smaller triangle, and you can see the mesh actually has divided the smaller triangle into only 1, 2, 3, and 4 parts. So this is not that much kind of dense mesh, okay, but still the meshing quality, if you improve, if you try from here, if you try to improve the meshing quality, your computational time will increase exponentially. So we don't want that kind of complex computations, okay. And I think this is more or less about your, okay. So one thing, after the simulation of topological edge state, you go to this electric field and click on the surface here. Okay, I need to show you one thing. So this is the kind of the electric field distribution it will look like. You change it to the magnetic field, that is the HZ component, because T mode, we are analyzing the T mode. So you just click it on HZ, then click it like this. That done. Okay, here, let me show you this. So this is red. Yeah. So this will be the typical coupler here. This will be the tapered coupler, and say suppose this is the coupler here, out coupler, for out coupling the signal into the into the receiver part, the output port actually. And so this is the tapered coupler, okay. So this is the tapered coupler. So you can see that the field mode is actually symmetrical at this in the upper and the upper and bottom portion. So we are keeping the tapered coupler in the middle. We are not keeping it below, or we are not keeping it like this. Why? Because if we keep it like this, the whatever incoming field will come, it is actually symmetric, okay. And we are placing it symmetrically now, okay, with the field distribution that we have seen. So what will happen is that this incoming signal and this the field the eigenfrequency the field mode, okay, the eigenfrequency mode of the at this interface, it is also symmetrical because we have placed it symmetrically. So this two will have the field overlap. So this is known as the field overlap. Okay. So this field overlap will get maximized, and that's why a maximum amount of power we actually will couple to this structure, and that's why we do this kind of symmetry. So this placement of the tapered coupler is very important. So that will be seeing it in the second part of the video. So this was about all those state analysis. So I think our simulation has, yeah, it's almost done. So I will just show you how breaking the symmetry, this band gap opening actually it happens. So it's almost done. So just wait for 2 minutes. It will be over. So typically we keep it as finer option mesh quality because this is a single rhombus. So if you ever try to increase the mesh quality also here, so that will not hamper your simulation time, that will not drastically increase. But for topological edge state simulation, just make sure that you don't increase the mesh quality to a much higher value. So our simulation has got over. See here in this EMW also at k equals to 2, you can see there are two values. See, these two are these two are dissimilar values actually. Okay, so you can from there you can calculate the band gap also. So now you click on the 1D plot group. So just wait for 1 minute. So you can see here. So now you can see the band gap actually has opened, and inside that band gap an edge state will appear as you have seen in the topological edge state analysis. So this is called the zoom box. If you zoom it here, so you will be able to see the band gap range also, exact band gap range. What is that exact? So this is pretty much all about the band diagram analysis and the edge state analysis also. Okay. So in the second part, we shall be discussing about the entire photonic crystal, topological photonic crystal slab simulation, where we shall be discussing how the interface will behave as a waveguide, and then we can see the input signal will excite the edge state, and then the transmission will happen. Okay, so we shall be discussing it in details in the second part. Okay.
So thank you. That is all for this lecture. If you have got any query or doubt regarding this lecture, you mention simulation demonstration part 1 and photonic crystal MOOC on the subject line, and you can drop an email to me. Thank you.